Okay, so in the second talk, we are going to study the Lorentzian analogues of almost-Fuchsian hyperbolic three manifolds, which are called anti-de Sitter quasi-Fuchsian manifolds. So anti-de Sitter geometry is the Lorentzian analog of hyperbolic geometry in the sense that it is the geometry of Lorentzian manifolds of constant curvature -1. So the main difference is that now our manifolds are endowed with a pseudo-Riemannian metric of signature 2, 1 if we are in dimension 3. So we will have directions in which tangent vectors have positive norms and directions in which tangent vectors have negative norm. So let's first describe the model space. And you will find many similarities with the hyperboloid model of the hyperbolic space. So we start with R4 endowed with this bilinear form of signature 2, 2. And then we'll define anti-de Sitter space as the space of vectors with norm equals to -1. So this describes an hyperboloid in R4, and it's easy to verify that now this bilinear form of signature 2, 2 induces a pseudo-Riemannian metric of signature 2, 1 at the tangent space of each point. And so ADS3 is a Lorentzian manifold. And if we want to visualize it, then it's convenient to projectivize it so that it will live inside RP3, and then we can intersect it with an affine chart. And so we see that anti-de Sitter space actually is the interior of this quadric, which is the quadric of equation x squared plus y squared minus z squared equals -1. Okay. So exactly because the metric on this space has signature 2, 1, we can distinguish three different kinds of geodesics according to whether the tangent vector has positive, 0, or negative norm. So we talk about like, space-like, or time-like geodesics. And in this model, those are simply given by straight line segments, and you can distinguish the type of the geodesic by looking at how many intersection points you find between the quadric and the line segment. Another thing that we are going to use is the fact that inside anti-de Sitter space, we can find a totally geodesic copy of the hyperbolic plane. And this is simply given by the intersection of the hyperplane x3 equals 0 with anti-de Sitter space. And if you think about it a little bit, you see that this is exactly the projectivization of the standard hyperboloid in R3 embedded inside R4. And so this is the hyperboloid model of hyperbolic space. So for the isometry group of anti-de Sitter space is then identified with linear transformations that preserve the bilinear form of signature 2, 2, and we will be interested only in the identity component, which is PSO22, and this happens to be isomorphic to PSL2R cross PSL2R, and in fact, because of this exceptional isomorphism, that anti-de Sitter geometry is very much related to hyperbolic geometry, in particular the hyperbolic geometry of surfaces. And we will also consider the subgroup of PSO22 that stabilizes set-wise this totally geodesic copy of H2, and this can be identified with the diagonal inside PSL2R cross PSL2R. So it's still a copy of PSL2R that is embedded inside the isometry group of anti-de Sitter space as the diagonal. Okay, so we are then interested in anti-de Sitter Lorentzian manifolds. And we will construct these manifolds exactly like we constructed quasi-Fuchsian hyperbolic manifolds. So we consider a closed surface oriented and of genus at least 2, and we're going to consider a representation from the fundamental group of the surface into the isometry group of anti-de Sitter space, and we will construct then anti-de Sitter 3 manifolds by taking the quotient of anti-de Sitter space, or at least a subset of anti-de Sitter space in this case, by the image of the representation. So the basic example is again given by Fuchsian representations, which in this case are representations of the fundamental group of sigma inside PSL2R cross PSL2R that are actually contained in the diagonal. So you can write rho as rho 0, comma rho 0, where rho 0 is just a representation from pi 1 of sigma into PSL2R that is discrete and faithful. So this means that you are considering the same holonomy of a hyperbolic structure, and you are considering and you are embedding it inside PSL2R cross PSL2R in a diagonal way. So we saw that these subgroups will preserve the totally geodesic copy of H2 inside anti-de Sitter space. And so if you look at how this subgroup acts on anti-de Sitter space, you see that the action is actually totally geodesic, it is actually properly discontinuous on this domain omega. And so you can take the quotient of this domain omega under the action of the representation, and you obtain a anti-de Sitter 3 manifold that is diffeomorphic to sigma cross R, and where the Lorentzian metric is the warped product between the hyperbolic metric with holonomy rho and the metric dt on R. Okay, so also in this case, we have the same kind of phenomenon that we saw for Fuchsian hyperbolic manifolds, where we have a totally geodesic plane that is preserved by a Fuchsian representation, and then the quotient manifold is completely determined by the hyperbolic metric on the surface, and it can be written as a warped product. Okay, so now we are interested in more general representations called quasi-Fuchsian. And so those are representations in which the projections onto both factors are discrete and faithful. So they don't need to be the same representation into the two factors, but they need to be discrete and faithful in both factors. And so we define the space of quasi-Fuchsian, anti-de Sitter quasi-Fuchsian representations as representations that are discrete and faithful in each factor up to the action by conjugation of PSL2R cross PSL2R. And so you immediately see that so such a representation is simply given by a pair of discrete and faithful representations into PSL2R, but those are exactly the holonomies of hyperbolic structures on a closed surface. And so we have an identification between the space of quasi-Fuchsian anti-de Sitter representations with two copies of Teichmüller space. And so we can really see that these representations behave like Fuchsian representations because their limit set is still a meridian in anti-de Sitter space. We can still find a domain in which the action is properly discontinuous. And if we take the quotient, we obtain a manifold that is diffeomorphic to sigma cross R and is endowed with a Lorentzian anti-de Sitter metric. Exactly like it happened for quasi-Fuchsian hyperbolic manifolds, in this case, the metric will not be a warped product in general. So you can't write the metric explicitly, okay? And we are interested now in studying surfaces embedded in anti-de Sitter space, exactly like we studied surfaces embedded in hyperbolic 3 manifolds. So in this case, in order to do sub-Riemannian geometry, we need an extra condition on the surface that we are considering. So we always require the surface S inside an anti-de Sitter 3 manifold M to be space-like, meaning that the induced metric must be positive definite. So we must have a Riemannian metric on the surface. And this condition is enough in order to define all the usual tensors, the usual quantity that we already saw in hyperbolic geometry. So we can define its first fundamental form, which will be an induced Riemannian metric on S. We can define the unit normal, which now will be time-like because of signature reason. So the orthogonal direction must always be negative definite because the tangent plane to the surface has already a positive definite metric, and the metric on the ambient space as signature 1 to 1. And we can define a shape operator, and we can define a second fundamental form exactly like we defined them in hyperbolic geometry. And now these tensors are related by the Gauss-Codazzi equations. So the Codazzi equation is exactly the same equation that we saw in hyperbolic geometry and is also true for surfaces in Euclidean space. Whereas the Gauss equation is a little bit different. So this term -1 comes from the fact that the metric in the ambient space has constant curvature -1. And what the main difference between this Gauss equation and the Gauss equation that we found in hyperbolic geometry is this -1 in front of the determinant, which is determined by the fact that the unit normal has now negative norm. So if you go through the proof of the Gauss equation, you will see that the fact that the normal direction has negative norm changes the sign in front of the determinant in the Gauss equation. And then we say that a surface is maximal if the trace of the shape operator is 0. And again, this implies that the second fundamental form is then the real part of a holomorphic quadratic differential. So in this case, we talk about maximal surfaces because those are locally area maximizers. And this fact, again, comes from the fact that if you look at the variational problem for the area, the fact that the normal direction has now negative norm implies that the second derivative will be negative of the area functional will be negative, and so these surfaces will be local maximizers. Okay, so we have this general result by Barbeau, Began, and Zegib that says that every anti-de Sitter quasi-Fuchsian 3 manifold has a unique embedded maximal surface, and moreover, this maximal surface has always principal curvatures between -1 and 1. So this means that actually anti-de Sitter quasi-Fuchsian 3 manifolds behave like almost-Fuchsian hyperbolic manifolds because we always find a unique embedded surface of constant curvatures, mean curvature 0, and the principal curvatures are always between in the interval -1, 1, which is something that in the case of hyperbolic geometry we had to impose and we had to restrict to a particular class of quasi-Fuchsian manifolds satisfying this property. In anti-de Sitter geometry, instead, this property is always satisfied. And so this means that in this context, we can actually parameterize the whole component of quasi-Fuchsian, the whole deformation space of anti-de Sitter quasi-Fuchsian 3 manifolds using the embedding data of the maximal surface. So we can consider the map that associates to a anti-de Sitter quasi-Fuchsian 3 manifold the embedding data, in particular the conformal class of the induced metric and the holomorphic quadratic differential determining the second fundamental form of the unique maximal surface embedded in the manifold M rho. And this map turns out to be a diffeomorphism. So in particular, you can completely determine the metric on the Lorentzian manifold M rho just by looking at the induced metric and the second fundamental form of the maximal surface. And actually, the induced metric is completely determined by just its conformal class and the quadratic differential Q. So it's exactly the same picture that we saw in hyperbolic geometry, but in hyperbolic geometry, we had to restrict to a particular class of quasi-Fuchsian manifolds. So in some sense, these manifolds in anti-de Sitter geometry actually behaves even better. Okay, so in the main result that we saw about almost-Fuchsian hyperbolic manifold was about the global geometry of the deformation space, which was very rich. We could define on the space of almost-Fuchsian manifold a hyperkähler structure. Okay? So we have an analogous result in this context, but first I have to define for you the analog of a hyperkähler structure in this mixed signature context. So first of all, we have to define a paracomplex structure. So a paracomplex structure on a manifold M is a bundle endomorphism, so is an endomorphism of the tangent bundle of N with the property that J squared is equal to the identity. And moreover, we require the eigendistributions for the plus or minus 1 eigenvalues to be integrable and of the same dimension. So this means that the dimension of the manifold must be even, and we call the pair Nj just a paracomplex manifold. A paracomplex manifold is then parakähler if there is a pseudo-Riemannian metric of signature Nn that is compatible with the paracomplex structure J. And by this, I mean that if you act, so G of Jx, Jy is equal to negative G of Xy for every X and Y tangent vectors. And moreover, the two-form omega J is symplectic, so it's closed and non-degenerate. So a parakähler structure is the analog in this pseudo-Riemannian context of a Kähler structure in a complex geometry. And then we have a para-hyperkähler structure, which is a quadruple Gi, J, and K, such that I is a complex structure compatible with G. So this means that I acts like a rotation for the metric G. The two-form omega I is symplectic. So if you want, this means that G and the pair Gi defines a sort of pseudo-Kähler structure where the metric is not a Riemannian metric, but is a metric of signature Nn, but it has the same properties as the usual Kähler metric in a complex manifold. The pairs Gj and Gk are parakähler structures, and K is the product of I and J. So if you are familiar with that, this means that I, J, and K satisfy the relations of paraquaternionic numbers, exactly like I, J, and K in the case of a hyperkähler structure satisfy the relations of quaternionic numbers. Okay, so the result I recently proved together with Filippo Mazzoli and Andrea Seppi is that the space of quasi-Fuchsian anti-de Sitter 3 manifolds has a natural mapping class group invariant para-hyperkähler structure, Gij, and all these elements actually are very natural in the sense of anti-de Sitter geometry, because so the complex structure I comes from the natural complex structure on the cotangent bundle. So like we saw in the previous lecture, Teichmuller space has a natural complex structure, so the cotangent bundle has a natural complex structure as well, and I is exactly that complex structure inherited from the identification between quasi-Fuchsian anti-de Sitter manifolds and the cotangent bundle using the embedding data of the maximal surface. Then the para-complex structure J is the natural paracomplex structure on the product of two copies of Teichmuller space. So we saw in the beginning of the talk that quasi-Fuchsian anti-de Sitter manifolds can be identified with the product of two copies of Teichmuller space. So under that identification, the natural paracomplex structure on Teichmuller cross Teichmuller becomes the paracomplex structure J, and the natural paracomplex structure on this product is simply the bundle endomorphism that acts like the identity on tangent vectors to the first component and negative the identity on tangent vectors to the second component. Then the metric G restricts to a multiple of the Weil-Peterson metric on the Fuchsian locus. So the Fuchsian locus is given by manifolds whose quasi-Fuchsian manifolds that are actually Fuchsian. So their representations is completely determined by a representations inside PSL2R, and so the deformation space of those manifolds can be canonically identified with Teichmüller space, in which we have the Weil-Peterson metric. The symplectic form omega I and omega k are the sum and the difference of Goldman symplectic forms on the PSL2R cross PSL2R character variety. So if we interpret quasi-Fuchsian manifolds as being a connected component in the PSL2R character variety consisting of representations in which both the projections onto both factors are discrete and faithful, and moreover, the area of the maximal surface is a potential for the form omega j, exactly like we saw in the context of hyperbolic manifolds, where the area of the minimal surface was the Keller potential for one of the symplectic forms. So what I wanted to say in this, so the message I wanted to convey in this lecture is that anti-de Sitter geometry is very rich, and it has a lot of connections with hyperbolic geometry, and actually these kind of manifolds behave even better than hyperbolic 3 manifolds. So I hope you are now more curious about anti-de Sitter geometry, and I can answer all your questions during office hours. Okay, so thanks for your attention.